A whole-body radiation dose near 4 sieverts is often used as the point where roughly half of exposed people may die. But 4 sieverts does not mean a dramatic flash, instant collapse, or a body filled with heat. The energy involved can be astonishingly small. If 4 grays were absorbed evenly by a 75 kilogram person, the deposited energy would be about 300 joules, roughly the work required to lift 30 kilograms by 1 meter. The danger is not the total energy. It is where that energy lands. Ionizing radiation transfers energy into atoms and molecules along microscopic tracks. Those tracks can break chemical bonds, damage DNA, and kill cells that the body cannot easily replace. Bone marrow, the lining of the intestine, and other rapidly dividing tissues are especially vulnerable. A dose that barely warms the body can destroy the systems that make blood, control infection, and repair tissue. Radiation is lethal because it deposits ordinary energy with extraordinary precision. 2 units describe different parts of the problem. The gray measures absorbed energy. 1 gray is 1 joule deposited per kilogram. The sievert tries to represent biological harm by accounting for the type of radiation and the tissues exposed. For penetrating gamma rays or X-rays spread through the whole body, gray and sievert values can sometimes be numerically similar enough for a rough comparison. But they are not interchangeable in every situation, especially for neutrons, heavy ions, or exposure limited to one organ. That is why a medical scan and a radiation emergency cannot be compared by one frightening number alone. The CDC lists a typical chest X-ray near 0.1 millisievert and a typical CT scan near 10 millisieverts. The average person in the United States receives about 6.2 millisieverts per year when natural background and medical exposure are combined. These doses are not zero risk, but they are separated enormously from an acute whole-body dose measured in thousands of millisieverts. Acute radiation syndrome requires a large penetrating dose delivered to most of the body in a short time. CDC clinical guidance places the usual threshold above about 0.7 gray, although mild symptoms may appear from roughly 0.3 gray. Early nausea or vomiting can be followed by a deceptive latent period in which the person appears to improve. Underneath that calm surface, stem cells in the bone marrow may be dying. As dose rises, the failure changes. Around 4,000 millisieverts, the CDC uses a rough benchmark of 50% lethality. The number is not a cliff. Age, health, dose rate, burns, trauma, and medical treatment all change survival. Between roughly 6 and 10 grays, gastrointestinal syndrome becomes dominant. The intestinal lining fails, causing severe infection, bleeding, and dehydration. At 20 to 50 grays or more, damage to the nervous and cardiovascular systems can lead to death within about 48 hours. Timing matters as much as the total. For grays delivered across the whole body in minutes is completely different from smaller exposures spread across months or focused on a tumor. Healthy tissue can repair some damage between separated doses, which is why radiation therapy is divided into carefully planned fractions. The same arithmetic total does not guarantee the same biological outcome. Whenever someone asks for the single lethal radiation dose, the honest answer must include how fast, what kind, and where. Earth protects us before any spacecraft shielding begins. The atmosphere absorbs much of the incoming particle shower, while the magnetosphere redirects many charged particles. The International Space Station still sits inside the upper atmosphere and much of Earth's magnetic protection, yet its crews receive far more radiation than people on the ground. NASA educational material gives an annualized ISS range of roughly 200 to 400 millisieverts, depending on orbit, solar activity, shielding, and mission conditions. NASA therefore treats radiation as a career risk, not only an emergency. Its current human spaceflight standard limits an astronaut's total career effective dose from spaceflight to 600 millisieverts. The limit is designed around keeping the added mean risk of cancer death below 3%. NASA also limits effective dose from a single solar particle event to 250 millisieverts. Neither number is an instant lethal dose. Both are warnings that accumulated exposure can end a career long before it causes acute sickness. Beyond low Earth orbit, the protection becomes thinner. Solar eruptions can accelerate large clouds of protons, producing a dangerous dose over hours. Galactic cosmic rays arrive from outside the solar system with even higher energies. A spacecraft cannot simply wrap the crew in unlimited metal. High-energy particles striking heavy shielding can create secondary radiation. Mission designers combine aluminium structure with hydrogen-rich materials, water, food, and dedicated storm shelters, then use space weather monitoring to move the crew before a solar event peaks. Mars turns this engineering problem into a mission limit. NASA's radiation assessment detector traveled inside the Curiosity spacecraft and measured the environment during the cruise and on the Martian surface. Using those data, NASA estimates that a human Mars expedition with comparable spacecraft shielding could deliver about 1 sievert, with roughly equal contributions from the journey out, the surface day, and the journey home. That is not an acute 4 sievert blast. It is a slow exposure large enough to exceed NASA's current 600 millisievert career limit. The central problem is not that astronauts cross one invisible line and die. It is that every extra month adds damage that cannot be completely shielded away. Better forecasting can reduce exposure to solar storms. Water walls and hydrogen-rich materials can improve a shelter. Faster propulsion can shorten the trip. But galactic cosmic rays remain a background that follows the crew through the spacecraft and across the surface. So how much radiation does it take to kill a human? For an acute penetrating whole-body exposure, 4 sieverts is a useful rough 50% benchmark, not a universal death sentence. Around 1 gray, radiation sickness becomes possible. At 6 to 10 grays, survival becomes unlikely even with treatment. Spaceflight usually operates far below those acute levels, but the accumulated cancer and tissue risk becomes mission-defining. The number that kills instantly is dramatic. The number that quietly limits where humans can travel may matter even more.